All right, everyone, welcome. Today, we're diving deep into one of the most incredible stories inside our bodies, the family tree of blood. I mean, think about it. Every single cell, from the ones carrying oxygen to the ones fighting off bacteria, they all start from one single place. Let's trace that story.
Okay, here's our game plan. We'll start at the very beginning, then branch out into the two main families, the myeloid and lymphoid lines, and we'll wrap up with the high-yield clinical stuff you absolutely need to know. Let's jump in.
First up, the origin of blood cells. We're going to meet the ultimate ancestor, the cell that starts it all.
So, this whole incredible process is called hematopoiesis, and it all starts with this one almost magical cell, the multipotent hematopoietic stem cell. It's tucked away deep inside our bone marrow, and you can think of it as the ultimate ancestor, the progenitor that holds the blueprint for every single blood cell your body will ever need.
And right at the beginning, this master stem cell makes a huge decision. It has to choose one of two paths, splitting into two massive family lines. First, there's the myeloid lineage. These are your first responders, your oxygen carriers. And then there's the lymphoid lineage. Think of them as the highly trained special forces of your immune system.
Okay, let's dive into that first branch, the myeloid lineage. We're talking about the first responders and the all-important oxygen carriers.
All right, first up, meet the neutrophil. These guys are the infantry of your immune system, the most common white blood cell you have. When there's trouble, they are the absolute first to show up. And that weird multi-lobed nucleus, it's not just for show. It makes them super flexible, so they can literally squeeze through the cracks in your tissues to get to the fight.
And they don't show up empty-handed. Their granules are basically toolkits full of destructive enzymes to chew up bacteria. So how do they know where to go? Well, they follow chemical signals, chemotactic agents like IL-8, which act like a GPS, guiding them straight to the infection. Now, here's a key clinical point. If you see a neutrophil with too many lobes, say 5 or more, that's called hypersegmentation, and it's a huge clue for B12 or folate deficiency.
Okay, this is super important clinically, so listen up. A left shift is when your bone marrow gets so desperate fighting an infection that it starts sending out teenage neutrophils, the immature ones. It's like calling up the reserves. But a leukoerythroblastic reaction is way more serious. That's when you see both immature white cells and immature red cells in the blood. That's a huge red flag that something is seriously wrong with the bone marrow itself, like it's being invaded by cancer or scar tissue.
Next up, the erythrocyte, or red blood cell. And honestly, it's a marvel of biological engineering. To do its job better, it literally throws out its own nucleus. Why? To pack in as much hemoglobin as possible. This gives it that classic biconcave shape, which is perfect for maximizing surface area and for squishing through the tiniest blood vessels in your body. Pure efficiency. So how do we know if the bone marrow is making new red blood cells? We look for these guys, reticulocytes. They're basically baby red blood cells, fresh off the assembly line. They've still got a little bit of leftover RNA, which gives them a bluish color. And here's the clinical takeaway. If a patient is anemic but has a high reticulocyte count, that's good. It means the factory is working. But if the count is low, well, that tells you the problem might be with the factory itself. Okay, and then we have platelets. And get this, they're not even real cells. They're just tiny little fragments. So there's this monster cell in the bone marrow called a Megakaryocyte, and it literally just pinches off little bits of its cytoplasm into the bloodstream. Those bits are platelets, and their whole purpose in life is to rush to the site of an injury and form a plug. And they don't last long, only about 8 to 10 days. Here's a dumb but effective mnemonic: platelets. 8 days. Simple. Clinically, when your platelet count is too low, that's thrombocytopenia, you get these tiny little red dots on your skin called petechia. They're basically tiny little bruises from micro-leaks in your capillaries, and a key sign is that they don't turn white when you press on them.
All right, we've met the heavy hitters of the myeloid line. Let's move on to the specialists.
Now this cell is really cool. It kind of has a secret identity. While it's circulating in the blood, it's called a monocyte. You'll know it by its big kidney bean-shaped nucleus. But once it gets a call to action and moves into the tissues, it undergoes this amazing transformation into a macrophage. And macrophage literally means big eater, which is exactly what it does.
So these macrophages are the ultimate cleanup crew. They gobble up bacteria, dead cells, you name it. But they're also intelligence agents. They take pieces of the bad guys they've eaten and show them to the rest of the immune system. And here is a clinical pearl you cannot forget.
The lipid A on bacteria binds to a receptor called CD14 on macrophages. This is the trigger for septic shock. That binding event unleashes a cytokine storm that can be absolutely devastating.
Okay, when you see this cell on a blood smear, it's unmistakable. It's got that two-lobed nucleus, kind of looks like a pair of sunglasses, and these big, bright pink granules. When you see that, I want two words to pop into your head: parasites and allergies. That's an eosinophil. Those pink granules are full of a nasty substance called major basic protein, which is fantastic at destroying parasites, like worms.
So if your patient's lab report comes back with high eosinophils, how do you remember what could be causing it? Easy. Just remember the mnemonic Pac-Man eats. Parasites, asthma, chronic adrenal insufficiency, myeloproliferative disorders, allergic processes, and neoplasia. It covers all your bases.
Now, basophils and mast cells are super similar. Think of them as cousins. They're both packed with granules full of histamine and heparin, ready to kick off an allergic reaction. So what's the difference? It's all about location, location, location. Basophils are in the blood, while mast cells live out in the tissues, acting like local security guards.
All right, time to switch gears to the other side of the family, the lymphoid lineage. These are the brains of the immune operation, our adaptive immune system. Here we have the two main players of adaptive immunity. First, the B lymphocytes. Easy to remember. B for bone marrow, because that's where they mature. Their job is to make antibodies. Then you have the T lymphocytes. T for thymus, where they mature. These are the direct killers and the coordinators. You've got your helper T cells and your cytotoxic, or killer, T cells. One makes the weapons, the other does the hand-to-hand combat.
Okay guys, this is one of those rules that will save you on exams. It's the rule of 8. It's dead simple. MHC class 2 interacts with CD4 T cells. 2 times 4 equals 8. MHC class 1 interacts with CD8 T cells. 1 times 8 equals 8. You will never get this wrong again.
So what happens when a B cell gets the signal to go to work? It turns into this, a plasma cell. And a plasma cell is nothing short of an antibody factory. It's just churning them out. And you can always spot one under the microscope because of its very distinct look. It's got an off-center nucleus that looks like a clock face. That's a classic. All right, let's wrap this up by summarizing the most important high-yield clinical facts. Okay, let's run through these quickly. Neutrophil, left shift. Erythrocyte, remember that B12/folate deficiency gives you not just anemia, but also those hypersegmented neutrophils. Platelets, low count means petechia. Eosinophils, parasites and asthma. T helper cell, that's the CD4 cell that HIV targets. And finally, plasma cell, if it becomes cancerous, that's multiple myeloma. Boom, done. So, to wrap things up, I want to leave you with a question to chew on. We've just walked through this beautiful, complex system where one cell gives rise to so many different specialists. But where do you think it's most likely to go wrong? Which step in this whole process is the most vulnerable to a mistake? Because when you figure that out, you're on your way to understanding the basis of diseases like leukemia.